Hello, everyone, and welcome to Into the Terminal. Today, we're going to be covering file systems, but we're going to do things a little bit differently for this next few series because one of the key things for troubleshooting issues is knowing how things actually work so that when you have a problem, you can kind of diagnose where in how things work have things gone wrong, rather than just like peppering you with commonly caused things. We'll actually like build some depth of knowledge. Nate, why don't you jump us into the terminal and show us the tools that we're going to use today?
Absolutely. So I firmly believe that just knowing the solution to a problem isn't enough. And you need tools to diagnose problems. Just like, I don't know, if you were diagnosing an electrical problem, you need a multimeter, right? Maybe that's too deep for some people. But my point is, we've got tools to talk about. So first of all, when you're dealing with file systems, where do file systems usually live? On a disk. So it's really helpful to know what disks are actually present in your system. And there's a couple tools that'll let you do that. The one I like to use is lsblk, which is like an abbreviation for list block devices. lsblk will show you a tree of not just the devices you have, but what partitions are on them. And if they're mounted, it'll show you where they're mounted and whatnot. And you can see I've got a couple things mounted here, some of which is for a later demo. Ignore the man behind the curtain. The other one is block ID. So blkid. Similar output, except it'll also give you things like the UUIDs and some more information about what those different partitions are, right? And what, like how they're mounted and where they're mounted, things like that. So block ID. Another one is good old-fashioned mount. Now, mount, in my opinion, has gotten a little harder to read over the years. On older systems, it was very straightforward because all the stuff that was mounted was just like block devices. Now there's a whole bunch of virtual file systems and whatnot that go into play. So this is, in my opinion, not as easy to read as it used to be. However, it shows you everything that's mounted, right? So if you need to know what those virtual file systems are, this is where you're going to find them. But just looking for like, okay, where's DevSDB nowadays? Right, it's like buried in the output here. So, all right. So mount will also, if you just do mount without any options, it shows you the output that I just gave you. Mount is also the tool that lets you mount and, well, not unmount. There's another tool called unmount, which will let you mount and unmount file systems. So you saw before I had that mount for dev SDA3 on /mount. So we'll just use that as a guinea pig here. Right, this will unmount it. And now if I do mount, you'll see SDA3 is no longer in the list. Again, hard to see, right? But if there's another tool that we're going to talk about in a second called DF, I find that to be a simpler output, right? So you can see just the things that are mounted and how much space there is on them. So now, of course, we unmounted it. I'm going to remount it because it's important to have that thing mounted. Okay, so what I'm telling mount here is the type of the file system, which normally you don't have to do, but it's good practice. It'll generally figure out what it is that it's mounting. So I've told it type ext4 because I know that's the file system format that's on SDA3, and I'm putting it in /mount. And now if I did mount again, there it is in the list again. DF again will show me dev SDA3 in the list again. There's some handy command line options to DF as well. There's df-h, which says it gives me a human readable output to the space that's available and in use and whatnot. There's also the -i command line option, which tells me the inodes that are free, which we're going to talk about a little bit more in a future example here. Another great one for looking at space is du, right? Du will show you everything that's currently in the tree that you're in and tell you the size of it. There's also command line options that'll make it give you a human readable output. Sorry, du, not dh. Right, and now it shows it in K or meg or gig, right? If I go to /, it's a little easier to to look at. See, but it's really wordy, right? Because there's so much in the file system. There is max depth equals 1 will give you just the current directory structures, top level directories, and what their sizes are, right? So you can see, you can see probably an easier to read output. And then you can say, oh, it looks like user is taking up the most space. Then you can go into user and do the same thing, right? All right, and the last really interesting utility is lsof, which will list open file handles. lsof, and again, whole bunch of output. Usually I parse this through like grep or some other tool to try to filter out what I'm looking for. So I don't know if I wanted to like grep for, we're going to guess that something is probably open inside of Etsy. I don't know. It'll show you anything that's open from within whatever I grepped for, right? And that's, you know, how is your grep foo? How good can you filter using grep is basically how this how good you can get with that filter. All right, and those are the tools we talked about. Scott, did I miss anything you want to call out?
I just wanted to point out that if you could pull up that lsof one more time, the
Sure.
other fields of data, it shows you, of course, the file that is opened, but
Yep.
it also gives you the process ID of the thing that has it open and the name of the thing that has it open. And there's some other stuff
Right.
like what device it lives on. Other things are less important. But I think the key ones here are the name of the process ID of the process, and then further down the line, the actual file or directory that it has open.
Right.
But yeah, I think that'll do it. So
All right.
that's our toolbox for doing some troubleshooting with file system problems today.
I totally got
So,
a toolbox right over here. Should I get it out as a prop?
and pull out all the DFs that are in it. Yes.
There's a multimeter in there.
Not going to help us. But don't forget to like and subscribe. Stay with us. After the transition, we will actually go through some more conceptual, like how does this actually work? What is the flow of things that happen when I do different disk operations, so that we can get an understanding of like what normal looks like, so that when we do experience a problem, which we're going to do that later, we can use that understanding of knowing what it's supposed to work like to figure out what tools out of that toolbox we should pull out, and how to use them to help diagnose that problem. All right, so don't forget, like, subscribe, and stay with us as we transition into more about file systems and troubleshooting them. All right, so why don't we bring up our handy dandy whiteboard, and everyone can laugh at how horribly I draw and write things. But there are a couple of
We
things I
love your
wanted to walk.
whiteboarding, Scott. You're so good at it.
A couple of things I wanted to work through on the whiteboard. The first is a concept of mounting and collecting your file system together, right? So the whole point of the Linux file system hierarchy is that when we look at like slash or underneath of it, like slash home or slash user or slash var, to a user or process navigating the directory structure to get access to a file, they just want to be able to work a path down to the file or directory that they want and then do stuff with it. In reality, as administrators, we know that this directory structure is actually built out of component devices. So it might be that var here is actually stored on a disk that's dev SDB4. And inside of dev SDB4, we've applied a file system format, right? So we formatted this space so that we could effectively store files and retrieve files from it, because nobody really cares about what their file system is, whether it's XFS or ext3 or ext4 or Btrfs. No one really cares. Well, okay. Conan
Some
Kudo
people
cares,
care.
but most people don't care unless they put something in a file system and they can't get it back out again. Then they really care about file systems and devices. All right, so we're not going to go into all the different file systems and the benefits of choosing one over another. Sufficient today is saying, hey, down on DevSDB4 here, there's actually like places where we can store data, and there's places where you can store file metadata, and there was probably more data down in here. You can't even read when I write more. It's just like a scribble. And overall, this thing has some like finite disk space, right? Maybe when we created this partition devsdb4, we said it should be 15 gigs of space. So when we put things in var, we're actually using some of that 15 gigs of space. And down inside of that file system format, there's data blocks. We're actually storing the file contents. And then there's a thing called an inode, or for lack of a better word, a file pointer, that will track things like its metadata, right? What data blocks store the actual contents of this file? Like, give me the addresses of those data blocks. What are the permissions on this file? Who owns this file? What are the SE Linux contexts of this file? All that stuff gets stored in the inode, which tracks all the metadata for the file that has been placed in the data blocks of this file system. All right, so just to wrap up on this small bit here, your directory structure is actually a collection of devices. Could just be one, but could be many. And it's supposed to be invisible to your users and processes, right? They just need to go into home and their directory, and there are all their files. They shouldn't need to care that those files live on this disk drive versus that disk drive, or it's a partition, or it's a logical volume, or it's stored on a stand somewhere. Like, they shouldn't care about the back-end mechanics of where that file lives. Us as the operating system people or system administrators probably need to care, but users and processes don't need to care. All right, so that's one thing. We have this file system format. The other thing to think about is if we actually like look more closely at what that looks like, right? So here we are with var, and underneath var we have things like the log directory, and underneath there we have actual files and subdirectory. What's another one? Right, and more stuff underneath of there. Well, if we look at a ls-i, it'll tell me that inside of this directory, var log, maybe messages is inode number this, and the HTTP directory is that, and fail log is that. And what this is really telling us when we look at the inode number is that over here in my actual disk drive, inside of the inode table, which is a segment of the disk space that's been allocated to store file metadata, there's actually a listing for inode 13573. And on this table entry for the varlog messages file, which is inode 13573, we have things like permissions, user owner, and SE Linux contexts, file system ACLs, file attributes that are added to this file. Like, there's all kinds of stuff here in this this metadata. And then at the very end, we actually have pointers down to the actual blocks on our device that store the contents of our log messages file. And so when we access a file, like we use the less command to less varlog messages, So what happens is the less command is executed. That tells us that we need to look up that inode, because that's going to tell us whether we can or can't access this file. Right? So it comes over here to our inode entry, and it looks at that metadata like the permissions. So it looks at who we are and looks at the permissions on the file to decide whether we are or are not allowed to open the file with less command. And it'll look at the SE Linux context and decide whether our less command is or is not allowed to access the file because of its SE Linux context and the context that's stored on this file. It'll look at things like file access control lists to decide whether we can access it or not. And if all of that stuff works out and it turns out that, yes, we're authorized to look at this file, then we'll get a bunch of disk IO requests to go down to all these individual data blocks and grab them and reconstitute them and put them into the less command as input. Right? So that's what happens when we access a file. Well, what happens if we create a file? So down here, I create my file. I just touch it. So if I touch it, I have to create an entry for it. So a empty file will have an inode number assigned to it. And up here in my inode table, there will be an entry created for 17357. And it'll get some permissions assigned to it, which will be the default file permissions according to the UMask of the user that creates it. The ownerships will be established. The SE Linux context will be created based off of where the file was created and the SE Linux policy. And then if I was actually like storing data, it would go out and start allocating data blocks to store the file's contents, right? So if I made a copy or I redirected data into this file when I created it, then it would go out and actually represent that data in the data blocks of my device. But I said I was making a 0 length file, right? I just touched it. And so at this point, like what's over in here is the space to store all those pointers to our data blocks, but there's no listings there because we haven't actually created file contents yet. Similarly, if I delete a file, so I come in here and I use rm to delete this file. Well, then what happens is we come over to its inode over here, and assuming that we're authorized to perform this deletion, it'll go ahead and wipe out all the data blocks that are on disk that are associated with that file, right? And it doesn't wipe them out, it actually marks them for reuse, right? So the data is still actually intact, but they are available to be reused for the file system. And then it will mark this guy, the inode table entry, for reuse as well. So the inode table entry is still there, all the data is still in place, but it has been tagged so that if somebody else needs an inode number, this one is now available and it can be overwritten with fresh data for a new file. So that's a little bit on how file systems operate at the low level of like individual file representation.
Sorry, Scott, can you
All right.
repeat all of that? I was busy chatting.
Well, and that's what I was going to ask is, are there any questions that that I should take a look at here?
There was a little back and forth about what boiled down to what is the base size of a installation of RHEL 8 was the example, but I looked at my lab and Rick in chat looked at his lab. I got one from RHEL 9. He got one from RHEL 8. I think we have it pretty well covered. And really the answer is it's a couple gig, but it really comes down to what you installed, right? Because the RHEL operating system has so many options that you can install at install time. A minimal install is a couple gig, but you can get crazy big depending on what you chose to install at install time, especially if you like those graphical interfaces, Scott.
A minimal install is actually not a couple of gig. It's some megs, because a minimal install is about 300 packages, and that's it. But of course, you also probably want to store files on that device too. So you need to make your
Right.
file system big, so you have some free space to store your files as well. So you could probably get away with a couple of gig, and that'll give you enough space to install that 300 packages. and then have a little bit of space to store additional files and content on the machine. But yeah, it'll depend on what you install and how much stuff you want to store on the machine long term. All right. So that being said, now we kind of understand the flow of like how file systems interact with files and how processes interact with file systems. So Nate, why don't we take a look at some common problems, and we can figure out how to better isolate where we should be looking and what tools out of our toolbox we should use for that thing.
Sounds good. All right, so we're back on my lab machine here. This is the same one that I was using to try to get that answer to how how large an install of RHEL is. But at any rate, all right. So I've got this mounted file system. You saw it earlier when I was looking at some of the tools that that we were showing off. But it's under /mount, and I've noticed that if I just try to make even an empty file, it tells me there's no space left, right? So we're going to start troubleshooting by checking to see if there is, in fact, any space left. And if we use df, we see that, yeah, this is a pretty small file system, but it says there's only 3% in use. So why the heck can't I make a file? So if we go back to what Scott was talking about earlier, now, I don't know, first of all, Scott, anything you would try other than, because I know exactly what to go to fix the problem. And to be honest, I already know how to look for what the problem is. I was trying to think of other things that might help inform it, but really just the knowledge of how the file system works is what's fueling this.
Yeah, so we know that there are two aspects of a file system, right? There's the data used for storing file contents, and I can see that that's not what's causing your out of space error. But there's another component that is a limited quantity, which is what?
Right. The inodes, which is exactly what you were just talking about. It's almost like we were leading into that. So if we do, I mentioned earlier the df-i flag, but you might have noted that I did not use it because it would have just totally blown this out of the water, because that's exactly what's wrong. You can see that if we look for the inodes on /mount, that they are completely exhausted. And it's because it's such a tiny file system. There's only 128 of them to begin with. Now, there's options you can pass to MKFS when you're creating a file system that tell it how many inodes to allocate, or at least what percentage of inodes it should allocate. So if you have a file system that needs a ton of little files, which in this case, the exact way that I caused this problem is if we go into directory number 2 instead of directory number 1, I've got a bunch of empty files in here that are just numbered, and you'll notice that they stop somewhere around 115. And that's because that's how many inodes were free when I started the for loop that created them, right? So if I just were to remove one of these, and then look, sorry, df, I keep doing that. There is no dh. There is no dh command, guys. Now I have one free inode. That's because every file takes at least one inode. Now, I guess, what is it? If it expands past so many data blocks, that's when it takes more than one inode, correct?
No, so every file gets one inode.
Okay.
And if you
like I said, I was busy chatting when you were describing it.
Right. This is a great question, though. If you expand past the number of data blocks included in the inode data, it actually takes data blocks from the file system and converts them to additional data block pointers. And so this is a concept known as indirect file pointing. So the inode points to an indirect pointer, which is this block of additional pointers that then point to data blocks. And you can actually go several layers deep in that to store large files.
Right. And some file systems are smart enough. I think XFS does this, where if it's running out of inodes, it can actually dynamically allocate more. So that's
Correct.
one of the reasons we like XFS.
Yeah, and XFS is the default for Red Hat Enterprise Linux 7, 8, and 9.
Yep.
And it does dynamically create inodes, which is one of the reasons why you chose what file system for this demonstration, Nate?
ext4, because I don't think XFS would have even allowed me to make a file system this small.
Well, so that is true. But XFS would also make it really hard for us to demonstrate this because it would just keep converting data blocks into
Yeah.
inode sections so that we could keep making these tiny or very little data stored files.
Which I'm guessing we could still eventually exhaust, right? But it wouldn't be as easy. So,
So
yeah,
Nate, what's your
ext4 on my like 1 megabyte file system. I have a floppy.
what's your solution for running out of inodes?
The solution, there's a couple solutions, I guess. One would be, I mean, you have to plan ahead of time. If you're using ext4, you have to plan ahead of time and allocate more inodes if you know you're going to have a bunch of tiny files. And there's certain workloads that do make a bunch of tiny files. Some web frameworks do it. Some disk-based like storage and retrieval systems will make a bunch of tiny files. So those are things you're going to want to consider. And when you're creating the file system, you're going to want to say, allocate more inodes than you normally would. Or use XFS, right? A big enough disk that'll support XFS, use XFS, and then this will expand. Unfortunately, in the case where I'm at, unless you know something I don't, the only real fix is to either make a new file system and migrate to it, or delete some files.
So there's one more fix, but it is only really valuable if you have used an extensible device. So like if you were using logical management, for example, and you added
You
more
could extend,
space.
yeah.
Yeah. And when you extend, it actually will create additional inode tables when you extend. But again, like XFS doesn't matter because as soon as you extend, it'll just create inode tables as it needs when you start storing data there again.
Right, right. So yes, extending the file system would do it as well. I was trying to think of solutions that didn't, in this case, I can't extend it because there's no more space left on my disk. That's actually why it's so tiny. It wasn't just for demo purposes. All right, so did we have any questions about this? I did see chat scrolling by, but I can't really pay attention to it and run the lab at the same time.
Yeah, we just got a couple of things about, Thomas Jones guessed out of 9 nodes, which was very good.
Yep.
Some back and forth on XFS and people not knowing that it dynamically created inodes, which is excellent. And then Darth Vike said, I hope all ext something file system support is no longer around. And sadly, that is not the case. Because a lot of distributions still ship extended, usually type 4 file systems as standard. So there you go.
And it's, of course, still supported in RHEL at this point, right? I don't know how long that will be. I haven't seen a roadmap on when that's going away, but if it's going away.
Yeah, I think we'll end up keeping ext4 support for quite some time.
It was kind of the de facto standard for so many distributions for so long that, yeah, I don't imagine it going away anytime soon.
Yeah. All right, so let's take a look at another problem now that we've solved this one. All right, so here is my system, and we're going to use a couple of diagnosis problems. What the problem appears to be is when we look at our disk free, you can see that dev SDA2 there is 99% full. And how I was alerted to this is my monitoring system started sending me all kinds of pages and emails that this was a problem because it's about to be a real problem.
But is it 2 a.m.? Because that's relevant to the problem.
Yeah, yes, it's always at 2 a.m. So clearly we're almost out of disk space, and there's a couple solutions here. One is maybe I do a file system extension like we were talking about with inodes. That could work. But maybe this is like the only box that's like this because something went a little haywire. So the tools that I'm going to pull out of my toolbox are DU, so that I can figure out what is actually consuming this almost 20 gigs of space. All right, so I'm going to use DU, and we're going to type that. And I saw Rick had suggested this earlier in the show, which is one of our one-liners a couple shows ago. du pipe into sort, pipe into head. Sorry, I need to also tell it to do it over the entire system. There we go.
Working directory matters.
Yep. All right. So var, and specifically var log, is the biggest consumer space at almost 16 gig. So let's take a look at what's going on there. All right, so I'm looking here in var log, and I scroll up a little bit, and oh dear goodness, look at that guy! Like that's a lot of space. That's 16 gigs. So something
Yeah,
a little bit
and it's
crazy and start overlogging.
so weirdly named big file.
I
How
know,
would you ever
almost
find that?
easily find it. So right, easy enough. We're gonna delete that file. So we're gonna remove var log big file. Cool. And now if I df-h, everything's good, but wait, it's not. But if I du, well, I mean, var log's not showing up there anymore, right? Because you guys all watched me delete that file.
Yeah, well, obviously the problem's solved. Go back to bed.
Right. Except it's not, because we can see that slash is still 99% full.
No,
So
it's
here's
obviously
what,
lying to you. It has to be solved because you deleted the file, Scott.
yeah, right. So remember when we were going through and I said, when we delete the file, we mark all these things for reuse. Well, it turns out that we only mark it for reuse when no processes are still using it. If the process is still using it, then we don't know what they're using that file data, so we keep it around.
Yeah.
Except we've removed the entry from etcfs tab, or sorry, not etcfs tab. We removed the file entry from var log because you told us to remove it, so we removed it. But the system knows that there's a process out there that's still using it, and so it's keeping that file handler open and keeping that data in place, which is why, even though we deleted the file, 99% disk usage.
Yeah.
So there's a command that we can use. lsof.
The crazy thing is, while that thing's still open in memory, whatever process has it open can still absolutely read the data from it, even though you have technically deleted it, right?
Right.
I wouldn't count on that as like a recovery, but like if you did accidentally delete a file that's open, if you act quickly, you may be able to recover the data out of it, but depending on what's reading it, right?
Well,
if it's something that you could write out with.
Actually, we can still recover it now because the file is still intact and its file metadata and the inode is still intact. So as long as this is still open and we have the file contents all still intact, we could put it back into place. But that's not what we want to do in this example. In this example, we want to figure out what's using it and kill it off so it's actually deleted, and that frees up my file system space so I can go back to bed after being paged at 2 in the morning. So lsof shows me all the open files. But what I'm going to do is I'm going to lsof and I'm going to grep for that file name. Right?
So
and we can see
there was a comment which may have helped. It might actually help people in a situation where maybe they don't know what file was deleted. You can grep for the word deleted.
indeed,
So that's
you can
also
see
helpful.
it here in parentheses the file. But what we're told here is the process name. So the less command has this file open. It's process ID 2464. And then we get some stuff about where it's stored and how big it is. And then it's var log big file and it's been deleted. So if I want to actually delete this file, I will kill process 2464. That's kill -9.
I really meant it. I
That's
wasn't asking, right? You ever see
There
that,
we go.
that comic?
And now if we df-h, right? I was at 99%, but now I'm back down to a normal amount of file system usage.
Right.
So having this open file still there and having to be preserved by the system because an application is using it is what caused my file deletion to not work, because I wasn't able to mark all of those data blocks and inodes for reuse, or actually the one inode for reuse, because something still had that file open. I had to preserve it. All right. We have one other problem to fix today. And let me show you how it manifests itself. So if we do a SSH, right there, could not change directory to home RHEL. Well, that's weird. And it just drops this user into the topmost directory on the file system, right? Slash, which isn't
Scott,
great.
obviously this means you've been fired and they haven't finished locking down your user yet.
Yeah, could be. But like other files about this user, like let's grep. So this is the RHEL user's entry in Etsy password. It says, hey, yeah, home RHEL. So like this directory was created. Let's look at it. Let me go back to being root. There is nothing in home. Lost and found directory.
Obviously somebody wiped out your home directory. But however, that lost and found directory tells me one thing. This is a separate mount. So you can verify that, right?
I can. So we could look at df, right? We can see that dev sda3 here is mounted on /home. We could also look at the mount command and see that it's mounted on /home. And this goes into our conversation really early about how we accumulate the directory structure by attaching different disparate devices at directory locations. And so Nate has correctly sussed out that we've taken dev sda3 and we've attached it at /home. Unfortunately, we did that and there was already data in /home.
Oh no, you've erased all of the data.
I mean, that's the fear, right? Because when we look in /home,
says
it's
kind
empty.
of sarcastically and leadingly.
So, when we look there, like there's no data in /home anymore. And that's because it's obscured.
Right.
So when we mount a new device on top of a directory, when shell processes and things or applications go into that directory, they see the topmost device or the most recently mounted device on that directory location. And so if I simply unmount or umount, all my data is still there. And so what had happened was this was a directory and we had added users to this machine. And then somebody had the great idea that we would create a separate file system for home. And they created it and formatted it and then mounted it on top of /home without moving all the data from /home to the new file system first. And so by mounting that device on top of /home, it hid all of this content that was already there, so that it made it inaccessible for users like the RHEL user logging in or Lager, whoever that guy is, couldn't get access to their home directories.
I have a really important question here, though.
Yeah.
How many accounts does Eric really need on our lab machines? He's in here at least twice.
I think the answer is 42. But so by unmounting that device, we were able to kind of sever the connection between the home directory location and that other device. And then what we're left over with is all the home directory contents that were stored there before. And so this is something I see a fair amount where people are trying to do something like a migration, or they may have created a device and they mount it somewhere thinking that it's okay. And they cover up someone else's data, right? So like if you took this and mounted it at temp or opt, that would be probably not great for other people in the system. So Nate, there is a place where if we were trying to plan one of these migrations, we could temporarily attach it. It's like designed for temporarily attaching things on the system.
I think we used it in my example,
Yeah.
right?
So
/mount.
exactly. So we're going to try and mount SDA3. I would put it at the M&T mount point. But again, whatever is the most recently mounted device is what you're going to see when you go into this directory. So there it is. And we could do things like copy right? So now the RHEL user's home directory is there, right? And we would do that for all the users, but I'm going to call it good enough. So now that we've got the right data in place, now we can mount it at that other location. Oops. All right, now when I SSH RHEL at localhost, right, they're able to CD into that directory and get access to their files because we moved them to the new device. And then we took that device that has all the right stuff in it and covered up all the things we didn't need anymore. So knowing what devices are mounted in your file system hierarchy and what's stored on them is also something I see people struggle with. And hopefully this provides a little bit of clarity and fixes some problems.
Yep, and those tools we listed at the beginning will help you, if you walk into a system you're unfamiliar with, maybe you didn't build it, maybe you're new to the job, maybe somebody handed you an existing system. But things like lsblk and blkid and mount will let you sort of inspect the system before you've made any changes to try to determine what's mounted where and how it's mounted.
Yeah, and we did have one question that I wanted to cover from the audience earlier. So I'm going to go ahead and set up that situation.
Now I want to know what question. Can you tell us what question, Scott?
Yeah, it was a question from Fernando Rattaji, who asked, how do you fix read-only file systems?
Okay.
So if we look at the mount command, all right, we can see right here that my home file system is mounted read-only. And we can see that this is the case by actually logging in as that user again. Right, and we're told we can't do stuff because it's a read-only file system. All right, so the question was, how do you make that no longer read-only? So right here, that is the file system, and it's mounted on home, and it shows us a bunch of the options that it's mounted with. And you can notice that one of the options is read-only. So there are a couple ways to fix it. One is you can unmount the file system, which will detach it from your machine. But sometimes you can't do that because, like, if that user was logged, we would be told that the file system is busy and we can't remove it while it's in use.
Or maybe that's the web root of your web application, or maybe that's where your database lives or something, right? And you can't just unmount it. Yeah.
Right. You could reboot the machine maybe, but also that has its own problems, right? Because now you're taking it out of service and you may not be able to do that. So the other thing that you can do is there's an option for mount called remount. And remount is how you make a live change to the mount options on a file system that's mounted. And I'm going to make it read write.
Yep.
All right, so you can see down there, it's mounted read write. And if I actually log in as that person again, right? I touched the file. There it is. No problems. It's read write now. So mount-o remount, and you tell it the options that you want to use or you want to change on your currently mounted file system, and it'll do it live. Because when I don't always test, but when I do it in production.
Now, in the chat, however, there's an important point brought up by Billy, and that is that it's important to understand why it's read-only before you just make it read-write again, right? Especially with ext-based file systems. If that file system is dirty, if it failed the file system check, it'll automatically go to read-only mode. And if you just switch it back to read-write, there's a possibility you could cause damage to the file system. So you're going to want to look through logs and whatnot and figure out when it went read-only and why before you just go ahead and make it read-write. In this case, Scott knew it went read-only because he switched it to read-only. And maybe, that's just something that happened. But usually when you find a read-only file system, there's some underlying reason as to why it's read-only. And you're going to want to suss that out before you just make it read-write and carry on with your day.
And the other place where I see things dynamically change to read-only unexpectedly is if you're having disk failures and you've had enough failures of your disk that the kernel's like, whoa, there's something really bad going on here. It'll flip your file system to read-only to make sure that you're not trying to write data and losing it because you have bad blocks or stuff on your failing disk drive. Those are there's a very clear message that is provided by the kernel as a write all to all terminals that says that it's flipping it to read only. The other thing is if you look in the varlog messages file, you will see a ton of error messages referencing your specific disk device saying like seeks timed out, meaning it couldn't read data off of it, or writes timed out, meaning it couldn't write data to it. So like Nate said, like look in the logs, try and see if there's something else going on that caused that automatic flip to occur. But the other place where I see read-only happening is people will make file systems like user read-only because they don't want new stuff installed on their machine. But then they need to apply updates.
Right.
So they can flip it right, apply their updates, flip it back to read-only so that new stuff can't be installed on the machine. So there are like real reasons why one would choose to make things read-only and then not, and then back again.
Yes, that is true.
All right. So last question I see is Aaron asking about reducing XFS file systems. So you can reduce ext3 and 4 file systems. You cannot reduce XFS. And the reason for that is because we dynamically create inodes and stuff in a USB file system. So if we're reducing it, we don't necessarily know where the inode tables are stored for the files that are in use in the file system. With ext3 and 4, it actually creates blocks of inodes at specific places in the file system format. So reducing ext3 and 4, we know where those file pointers are stored, and then we can look at them and see if there are any files in there and copy them to other places as we're doing that reduction. So I'm sure that it's not impossible to do that with XFS, but people have chosen to not write doing that for XFS because it is challenging based on the nature of expansion for XFS.
Right. And the number of times I've had to reduce a file system, I could probably count on one hand. Like that I had a reason where I just absolutely had to reduce it. Most of the time you're expanding them anyway, right? So that probably went into that decision process. There are certainly valid reasons, like, oh, I just migrated a bunch of data. Now I want to take some of that space back. Maybe it's a SAN volume or something, and you want to give that back to your storage admin so they can allocate it elsewhere. So yes, there's valid reasons, but it's less common in my experience than growing a file system is. Usually data just keeps expanding, not contracting.
Yeah. And Aaron points out that it was on a system where he made choices at install time that he regretted later and then wanted to fix it.
Yep. That's another reason.
But if you discover that early enough, just rebuild the system.
Yeah.
That's probably the fastest route to get you where you go.
Probably do some weird juggling in rescue mode to make that happen. But yeah, you can't reduce the file system easily.
Yeah, I don't think you even want to try to do that.
Probably not, but if you're feeling adventurous.
Remember what I said, Nate? People get really salty when they put data somewhere and then they can't get it back again.
That's a good way to make it happen.
All right. So I think that does it for our prepared remarks today. Nate is maybe doing a show next week. I'll be out of the office. So I don't know whether Nate and Eric want to do a show or not. We'll find out.
We'll figure it out. There probably won't be a whiteboard though, because I don't think Eric or I have anything resembling handwriting that's even up to par with yours, Scott. There's a reason I chose a career where I get to type everything I have to communicate instead of write it.
Fair enough. So in 2 weeks, we'll actually do another one of these troubleshooting labs. So we'll like keep the series going because I think understanding how the mechanics work helped you a lot. When things go wrong, you know where to look.
Yep. And before we go, don't forget, we have a Discord community that's around both, well, basically the RHEL live streams, right? And there's currently a link there's a QR code right at the top of our live stream that you can scan. Pretty sure there's a link in the description of the episode too. So go check it out.
All right. Well, don't forget to mash that like and subscribe. Thanks for making it this far, and we will see you in another Into the Terminal.